So today we're looking at classifications of these root systems that we have been working with so far. And to start out, we're looking at the cartan matrix. The cartan matrix of our root system. So we start out by fixing and ordering of simple roots. The matrix with the ijth components being the angle bracket of alpha I and alpha j is called the cartan matrix. The cartan matrix of our phi, with its entries being cartan integers, which I think is a concept that we saw before. And we can look at, last time, a while ago, I drew out the 4 root systems in 2 dimensions. It turns out I think that's all of them in the 2-dimensional case, up to isomorphism in the sense that we defined earlier. So we have the cartan matrix of A1 with A1 being this. The cartan matrix of A2, as we drew it before, being 2, -1, -1, 2. The cartan matrix of B2 being 2, -2, -1, 2. And the cartan matrix of G2 being 2, -1, -3, and 2. Now, of course, the matrix is going to be slightly different depending on the order in which you determine roots, but that's not really important for any of the properties we need of this matrix. But we do know, however, we have that this matrix is independent of our choice of base, as the file group acts transitively. On the collection of bases. And we have that it is non-singular, as our delta is a basis of E. And that turns out to be all we really need. So we're going to let phi prime in E prime be another root system with base of, say, delta prime, if the entries of the cartan matrices line up. That is, the angle bracket of AI and AJ is the same as a prime I, a prime j for some ordering of the second base. Then the bijection, sending each root of delta to the root of delta prime, extends to an isomorphism or some phi, sending each e inner space to e prime, mapping basis onto a root system, onto the other root system, and preserving our angle brackets. Thus, the Cartan matrix determines the root system up to isomorphism, of course. And the proof, since our deltas is a basis, delta is a basis of E, and likewise for delta prime on E prime, there exists a unique isomorphism, vector space isomorphism, sending E to E prime such that phi of A prime is a phi of AI is AI prime. If A and B are in our root system, then we have that sigma of phi alpha of phi beta is equal to sigma of alpha prime of beta prime, which is beta prime, of course, minus beta prime angle bracket with alpha prime on alpha prime, which is phi beta minus the same thing without the prime symbols. So this gives us phi beta minus the angle bracket beta and alpha of alpha, which is phi of sigma alpha of beta, such that this diagram, which I'm going to draw in a second, commutes. And we have E, our isomorphism phi, sending it to E prime. And then we have the reflection generated by a root, sending E onto E. This is the same phi. And there's a corresponding map on E prime of reflection generated by the image of alpha. The respective Weyl groups, Weyl and Weyl prime, are generated by simple reflections. So the map of a sigma to phi of sigma of phi inverse is an isomorphism of the Weyl group onto the prime Weyl group, sending each sigma alpha to sigma of phi of alpha for all alpha in our basis delta. As each root beta is conjugate to a simple root say that beta equals sigma alpha, we have phi of beta is phi of sigma of phi inverse of phi alpha, which is going to be inside of our prime root system. And thus phi maps our first root system onto our second root system. With the reflection formula showing that phi preserves cartan integers. And we're done. So we have seen, thus we can recover our root system from its cartan integers and we can do this in practice. Which can be done explicitly. This isn't just like there exists a corresponding basis. Through, for instance, root strings. We start with roots of height 1, which are our simple roots. For any pair of distinct roots, the integer r for the alpha j string through alpha I is 0, which is essentially saying that alpha I minus alpha j is not a root. So our q in the other direction is the negative of the angle bracket of alpha I on alpha j, which is a cartan integer, which we know. This lets us write all roots alpha of height 2 hence all integers alpha with alpha j. For each alpha, which is a root of height 2, R can be determined easily for a j string through alpha, since alpha j can be subtracted at most once from alpha, and then we have q from R minus q is the angle bracket of alpha and alpha j. By the previous corollary, I believe, of the first lemma from the last video, we can get all positive roots this way. All right. Now we're on to another chapter, one which is going to involve a lot of drawing, so get ready for that. Now we're looking at coxeter graphs and Dynkin diagrams. If alpha and beta are distinct positive roots, then the angle bracket of alpha on beta with the angle bracket of beta on alpha is 0. Is not 0, lies within 0, 1, 2, or 3. Define the coxeter graph of our root system to be a graph with L vertices, where L is the rank of a root system, I'll make a quick note of that here. With the ith joined to the jth vertex for distinct I and j by angle bracket of ai alpha j times alpha j alpha I edges. And going back again to our 4 examples, we have that A1 times A1. These are all our diagrams on order of rank 2. Remember last time our 2-dimensional ranks. A1 times A1 is just 2 copies, 2 vertices with no edge. So last time it kind of ties into how it's just A1 times A1. A2 is then connected by a single line. B2, because these are all the 2D cases, we know they're all going to have exactly 2 vertices. B2 is 2 lines, and G2 has 3 lines. And in this case, it's pretty easy to see how this is exhaustive, since there's only there's only one possible place for an edge to be, and it can only be 0 through 3 edges, so we just exhaust all those possibilities, and that's everything. I think there's more conditions on this than just like the number of edges and vertices, but that's coming later, I think. The coxeter graph determines the angle bracket of alpha I and alpha j when all roots have equal length, and so these two things our two roots kind of commute within the bracket, if you know what I mean. If we have both lengths, we don't see from this graph which root is long and which is short. However, it says it can be proved that the coxeter graph determines the Weil group completely, essentially because it determines the orders of the products of the generators of the Weil group. Now, we only have this ambiguity if we have double or triple edges. So, whenever a double or triple edge occurs, in the coxeter graph of phi, we can add an arrow pointing to the shorter route. This lets us recover the cartan integers and hence the cartan matrix and hence the root system. So we call this new version the Dynkin diagram. If you look at the above diagram, we have B2 and G2 having double roots, having multiple edges. So B2 and G2, we have our two roots with a double link, and you just go like, yeah, it's pointing that way. Or G3, we have our two roots with a triple link, and we just go like, yeah, this one's the short root on the left in this case. Or a more involved example, I'm going to give a diagram for what turns out to be F4. So it looks like this, right? We've got a single link to there, we've got another root system here with a double pointing that way, and another pointing this. And this has a cartan matrix of, okay, for our first column, I'm not even going to write the brackets until we have all the numbers. First column, we have 2, -1, and then no links to the others. The second one, we have a -1 link backwards, 2 to itself, a -2 going forwards, and then a 0. For a third one, we have a -1 going backwards, 0 to the first one, -1 going backwards through this, 2 to itself, and then a typical -1 going forwards, and then 0, 0, -1, 2. So this is how we recover our cartan matrix from the Dynkin diagram. And this will help us once we understand these diagrams a bit better, this will help us in our classification of these things. But there's one more section, a pretty small one, we'll just push through here. It's really just like, it's a paragraph and then a proposition which proves itself. So this is on irreducible components. If you remember, our root system phi is irreducible if and only if phi cannot be partitioned into proper orthogonal subsets. Thus, phi is irreducible if and only if its coxeter-dynkin its coxeter graph, and thus its Dynkin diagram, is connected. So your coxeter graph, you're going to be able to split it into connected components in general. So we let delta be the union of a bunch of delta i's, be the partition of delta into mutually orthogonal subsets corresponding to the connected components of the coxeter graph. If each EI is the span of each delta I, then E is the direct sum of each EI. And that's actually the orthogonal direct sum. We also see that the integer linear combinations of delta I, which form roots, form a root system in EI. Whose Weil group is the obvious restriction, obvious subgroup of the obvious subgroup of the Weil group, that is the one generated by the reflections of these roots. Finally, each EI is Weil invariant. Since alpha not being in root I means the reflection of alpha acts trivially on EI, since it's going to be inside the hyperplane. So we can get by homework exercise, I don't bother doing, each root lies in an EI. So phi is the union of the obvious phi's. It comes with a obvious proposition. See that phi decomposes as the uniquely as the union of irreducible root systems phi in EI, such that E is the orthogonal direct sum of EI, as we have seen above. Alright, so this shows that we can classify the irreducible systems by the connected Dynkin diagrams, and so that is what we are going to be doing next time. I know videos are kind of being on the shorter side today. That's kind of just how things are pacing themselves out. So yeah.